And here we go. We have liftoff. Propulsion continues to be nominal.
R68 chamber pressure looks good.
Traveling up. Roger, planet.
Water towers, fly! Yes!
Tango down to nominal.
Fighting downside FT off. Bring in FT off. It's orange!
R45. Oh my god! Oh my god!
Decolage. Look at this! Put that in the big bag,
343 unfolds to go.
Indeed.
We rise together, back to the moon and beyond.
The methane would be igniting with the flare, correct?
Yikes. You bet. We don't need any more of these.
All right, folks, you know the drill. We have a very important show for you today. It's Intrepid Museum's Astro Live events, supported by the New York Space Grant Consortium here. You know me, my name's John, but we are going to have a very important discussion today. We're going to talk about space shuttles and crew capsules and the safety of human beings that are flying on these things. And a bunch of us like to play armchair mission control, right? We have opinions and we like to post online and all this sort of stuff. But not a lot of us have experience with actually making these decisions for ourselves or for others. So it's easy for us to say this, that, or the other sort of stuff. But what goes through the mind of an astronaut that's deciding to walk across that crew plank and get aboard, say, a space shuttle? The most complicated machine ever built by humans. Maybe not the most safest machine built by humans, sometimes built by the lowest bidder. But how do you make that decision to walk across that plank? What goes through your minds? What experience do you draw on to make sure you can make that in an informed capacity? And what happens when you're making those decisions for other people? It's not your body that's walking across the plank, but you've got 7 other folks, 3 other folks, 4 other folks, whichever capsule you're talking about, and you have to make that call for somebody else. Joining us today, we've got a very special guest. I see a lot of folks in chat already jumping in here. I know that folks are going to have a lot of opinions today. Post up your thoughts. Let us know what you think. We're going to do some live questions as well, but keep it respectful because we're talking about human lives here and the culture and engineering safety that lets us get these folks in and out of orbit successfully. Please welcome to the show Dr. Charlie Camarda here, 46 years at NASA, 22 years of that as a TPS engineering researcher over at NASA, knows the drill when it comes to, is it safe to get aboard a spacecraft? Charlie, how are you doing?
I'm doing great, John. Thanks for having me.
Hey, how'd I do with the intro? We good with the intro there?
Oh, very good intro. I'm glad you didn't give them my CV. We would
I
be
didn't.
halfway. Yeah.
We're going to let your experience speak for itself here, because not only were you an engineer with years of experience, you were also an astronaut, and you didn't get aboard just any space shuttle flight. You got aboard STS-114, the return to flight after the Columbia disaster, didn't you?
That's right. That's right. That was a day I will never forget, just like I will never forget February 1st, 2003, when we lost the crew. And so I was training in Russia when the accident happened. And we were very sad, but I was very angry because when I saw the launch, when I saw the piece of foam come off the external tank and strike what looked like either the bottom of the left wing or the actual wing leading edge, I couldn't believe that engineers and flight directors and program managers at NASA didn't know that was a critical problem.
Do you think they didn't know, or do you think they just really wished that it wasn't a critical problem?
Well, I think they listened to people that were telling them a story that didn't have any expertise and used very rudimentary analysis. I wouldn't even call it analysis. I mean,
Right.
the crater equation that they used to predict whether or not they would have serious damage. Sophomore in engineering school would not have used that to make a decision. They wouldn't even use it to gain any insight. It was a non-physics based solution. And what I struggle with to this day is 1,200 engineers at Johnson Space Flight Center. flight controllers, program managers that went through engineering school, how could they believe that analysis based on what I will show you as we go, as if the people want to see what they made the decision on, we could let them see that. But it was incredible. It was incredible.
We've got an entire show here, 90 minutes, y'all. So we're going to deep dive into a lot of this stuff. Well, let's start off here, Charlie. You're selected for the crew. It's the return to flight. You have a deep understanding of how thermal systems work. You knew what happened to that previous flight. What are you thinking? Like, what goes through your mind when you decide, you're like, hey, all right, NASA, you're sending me on this craft. I guess I'll go ahead and get aboard it and let's do this mission. How do you make that decision?
Well, see, I was a research engineer for 22 years in this particular area in thermal protection systems. And so I knew what the risk was. I knew the risk of me losing my life flying in the space shuttle was 1 in 67.5. And based on that knowledge, we as astronauts sign up to take that risk, right? So as an astronaut asked to be on this mission, and it was a very important mission, and I did not know I was ever going to be selected for that mission, right? Because I was making a lot of noise at Johnson Space Flight Center. I really didn't think I would be selected for a crew, but my boss, Kent Rominger, the head of the astronaut office, let me work on these other teams, right? And so I knew what to expect because I had worked on 2 of the critical teams that not only discovered the cause, the technical cause of the accident, but also the team that developed repair techniques that we could fly in space to fix the vehicle. We had developed loads of technology and flight procedures in order for us to make our flight as safe as possible. And we had to test these technologies in order to make sure that the successive crews that flew on Space Shuttle till its retirement at STS-135 in 2011, that they would fly safe. So I thought when I was selected, I thought, wow, this will be great. We'll be testing some of the technology that me and my friends helped invent that I flew on and could test it out. And it was the perfect mission for someone that was a technologist, a researcher. It was very much an experimental flight.
We talk about informed consent, right? Like the person who's getting aboard this spacecraft, do they really understand the risk? And you were in a unique position because you had experience with the specific problem that caused the loss of Columbia, right? The thermal protection system problems. You had worked on that for years, decades, actually, quite literally decades. So in terms of informed consent, you really knew what could go wrong with the space shuttle, right? At least from a TPS perspective.
Right. And so remember, the Columbia Accident Investigation Board made its prediction, made its recommendations, made its decision, its findings. And what it said was that were 2 critical causes of the accident. The technical cause was the foam, right? And we tried to understand how that happened. But the other cause of the accident that they placed at the same level was the culture. And what I really knew was that the culture was still broken. And when we flew in space, our crew had no trust in the flight control team down on the ground, MOD, and we had very little trust. I had very little trust in the decisions being made by the engineers, not so much in their decisions, but whether or not their decisions would be heard and would rise up. And that speaks to the culture. So when we flew in space, I had a fallback position. I carried up in my crew notebook the list of all the names of the people that I relied on.
Right.
The Friends of Charlie network in my crew notebook.
Is that the crew notebook? Like you have the crew notebook with
that is the crew notebook that I took in space. And on the very first page are all the names of the key research engineers that I could call from space. We wouldn't have to go through mission control. I could talk to them directly. And it was one of those calls that saved our life.
So we talk about bureaucracy and we talk about inefficiency and important information or the signal get lost in the noise of program management, all this other stuff, right? Yeah. Some arguments that might have been what happened during Columbia. But when you got aboard, you basically wanted to get the truth from the horse's mouth, for lack of a better term. You had a list of people who you trusted and it wasn't necessarily mission control?
Absolutely was not mission control. And we had an agreement, our crew had an agreement with the team with the shuttle program, that
Right.
before every evening we would have a private phone conversation with the head of the astronaut office. No flight directors were allowed on the loop, just us and Kent Rominger, the head of the astronaut office.
Right. So one of the things that made you comfortable, A, you had experience with specific shuttle systems. You weren't flying blind. You knew how TPS works, how thermal protection works, and what risks there were. But you also had a list of people that were experts in things that maybe you weren't an expert in. And instead of going through the bureaucratic chain of command and chain of communication, you set it up so that you could directly talk to those people if there was a question, right?
That's correct. And so we had a serious problem. When we flew up in space, one of the maneuvers, remember the pitchback maneuver, the R-bar pitch maneuver, where Eileen Collins does a backflip 600 feet below the International Space Station, and they're filming and they're photographing the TPS on that vehicle.
Right.
What they noticed was a gap filler sticking out, and people on the ground had to make that decision. Is that safe to fly? It was only sticking out about an inch. And we had a report by one of the people from NASA Langley, Tom Horvath, and Scott Berry, aerothermodynamicists that I knew at Langley Research Center. And they sent up a report. I read the report. Eileen asked me, what do you think? And I actually called Tom Horvath from space.
Right.
And that's when we made the decision as a crew. It was absolutely necessary that we do this emergency EVA.
No kidding.
And that saved our life, because the flight after us, STS-121, had a little piece of gap filler sticking out towards the tail of the vehicle. They kept it in. They filmed it with IR cameras with a high altitude plane as it was coming in, and the gap filler remained in there. It tripped the boundary layer, as Tom Horvath and Scott Berry predicted, and caused excessive heating after that. So I'm pretty sure that our gap filler wouldn't have found its way to fall out. It would have been there and it would have caused problems.
So that's probably very specific to exactly where that gap filler is sticking out, right? But you have something sort of sticking into the hypersonic flow that changes how that flow works, and so it can create hot spots on the heat shield, I guess, if I understand it correctly.
Absolutely. It trips the boundary layer. And so these people are research engineers. These people are researchers. Some of them develop the codes to understand the hypersonic flow conditions. And that's what we rely on.
No kidding. So it's not a statistical analysis of, oh, well, we think this many times it might fail, et cetera, et cetera. It's somebody put a piece of hardware on a test and saw exactly how that worked in X number of different ways and figured out how that might affect the spacecraft.
Well, actually, they didn't have enough time to run the test, to my knowledge. Oh, this is great. You're showing Steve Robinson pulling the gap filler. Made that decision. This is the hero shot where Steve Robinson out on the bottom of a robotic arm. Now, I want to say one thing. The training team we have on the ground trained us tremendously. Jeff Sugar and the folks on our training team, we were trained for procedures and we could operate these conditions. And the team on the ground were running tests in the neutral buoyancy lab. People on the ground were doing the people doing the robotics, sent us up the plans to maneuver that astronaut, to maneuver the other robotic arm so that we could view it, to make sure we didn't hit anything. And they did it in a day and a half. Totally unscripted. That's a true network of teams approach for solving this. And that's where us working with the team of people on the ground that do what they do best to do this.
So that was like this, just to paint the picture for everybody sort of watching, right? The shuttle's approaching the space station. This was a mission to the space station. You're aboard the shuttle and it's coming towards the space station. But in order to get a good look at all the different sizes of the space shuttle, it does this sort of flip maneuver, right? And it sort of not rotisseries itself, but it just flips around so that. But
there it is, right there.
There you go.
Great, Kevin. This is Eileen Collins, first time ever. By the way, put a plug in for Eileen Collins' new movie, Space Woman, right? We just saw a preview of it. People watching this did not know what was going on our flight. How we almost lost our life several different ways, but they're taking pictures.
Yep.
John Phillips and Sergei Krikalev are taking pictures from the International Space Station. They're processed down on the ground with our imaging team,
Yep.
and then they show this tiny piece, this tiny thing sticking out. They zoom in on it, and people on the ground immediately start analyzing it. The people
Yep.
at NASA Langley,
Right.
wondering, is this going to trip the boundary layer? Is this going to cause problems?
Well, why did they have it there in the first place? Like, why put the gap filler in? Is it just required for liftoff? Is it required for reentry?
No, there's a very good reason. You have about 30,000 tiles on the bottom of that vehicle. In
Yep.
between those tiles are these felt-like materials, high-temperature felt-like materials, because the vibration during launch, these tiles could shatter and chip. Also, the air goes into the gaps of the tiles and
Yep.
causes excessive heating. So it's for two reasons.
So here, and Kevin, I don't know. I think we made the thumbnail from a picture of the gap filler sticking out. I don't think we circled it in the thumbnail, but do we? If we have that picture, we'll bring that up in just a second. But so you have the gap filler in there. Why is it okay to pull it out before reentry? Isn't it critical to the operation of the TPS?
That's another good story, right?
I'm asking for stories.
The people in the NBL had to practice doing this, because if it was stuck, God forbid we pull out an entire tile. Now, we had a repair kit to fix that damage, but you definitely don't want to test it for the first time on your mission. So
Right.
these people are doing these tests on the ground. What I don't think we told Mission Control was that the suited astronaut, when he went out, also had a hacksaw blade. Okay, I don't know if I should be telling this as a story, but just in case,
Yeah.
he could have potentially sawed that out, because you don't really want to go out there with sharp objects
Yep.
when you're in a spacesuit.
So
Yeah,
it's not just can we remove. Yeah, there we go. Okay, look.
yeah,
We actually
that's
have,
it.
there you go. I don't know if that's the thumbnail we ran, but we made that thumbnail and it's got the little thing sticking out there. So it's not just, it's okay to take it out. You can pull the gap filler out. It doesn't need to be there for reentry. But when you're pulling it out, you don't want it to be stuck on a tile and then you
Yeah.
damage the tile or crack it or do something
Exactly.
required for reentry, right?
Because you saw that orangey material, it's glued at the base.
Yep.
And God forbid you pull that out and the tile is a little loose, you
Yep.
could potentially pull an entire tile out. And we didn't know. Yeah.
So you said they had a repair kit. Did they normally bring tile repair kits? Was this a new thing that they
No.
developed after Columbia? Talk about that a little bit.
This was totally new. And so we had hundreds of people working in the program office trying to come up with repair kits for
Yep.
both the shuttle tiles and for the RCC leading edge. And we saw that they were having problems coming up with solutions. And the strategy for returning to flight did not include having a repair kit. That wasn't a necessary condition for us to fly in space, but I thought it was pretty important.
Yeah.
So when I saw that the program team was having trouble and they weren't coming up with a solution, I asked my boss if I could go start this team. I went in Don Pettit's garage and we came up with solution. Well, maybe Don doesn't want me to say I used his garage. We used an external laboratory. His garage was like a laboratory.
I'd believe it.
And the Friends of Charlie from around the country was sending us material that the shuttle program office wouldn't send us because they thought it was so critical that they needed it. But I had another source of Friends of Charlie that sent us material that we tested in his garage. And we actually came up with the solution for fixing a hole in the wing leading edge. And we handed that off to another team, NASA Langley, that Steve Scotty led. And by the time, what you're going to see is, when we did the actual full-scale test of that foam, it caused a pizza box size hole, 14-inch by 14-inch square hole in the wing leading edge.
Right.
So our crew in orbit didn't have the benefit of knowing how critical this was, and they didn't know. And so I feel for the crew on that mission, but the team on the ground didn't think it was any damage. It was a pizza box size hole. And what I'll show you later on is if you have the right team of people, and you know how to build a high performing team, and I talk about that in the second half of my book, because developing these teams and having the right people on these teams and having them able to work in what I call a research network of teams,
Right.
how to solve these problems rapidly using intelligent fast failure. You can get to the solution in 3 months' time
Yep.
when it took the entire agency over 30 years and they couldn't solve these problems.
What is over your shoulder there? I see in the background of your camera. What is that? A wing leading edge? What is that?
My first job in 1974 when I became an astronaut was looking at an alternate design for the wing leading edge for Space Shuttle.
Okay.
And so this is a metallic version of the wing leading edge. And the reason why it's able to survive the temperatures is because inside that, in the inner surface, are what are called high temperature heat pipes.
Okay.
And those heat pipes take the temperature from the nose, the stagnation region, and make the entire leading edge glowing the same temperature. And that causes the radiation area to be increased and the amount of heat coming out of the vehicle by radiation to reduce the critical temperature so you could use metallic heat pipes. And it wasn't selected because the program at that time didn't think it was mature enough.
Okay, that is the prototype over your shoulder of something that you designed that was a potential.
No, that was designed by McDonnell Douglas.
Okay.
And NASA had it in storage. And so when I became a junior engineer, we got it out of storage, and that was my first analysis and design analysis and test project.
Okay, gotcha. There's lots of questions coming through chat, and y'all, we have so much stuff to talk about. I'm going to hit a couple questions. You talked about a repair kit that y'all sort of developed on the side, almost an end around sort of thing. Talk about the repair kit some. Like if you were in space and there's a problem with the TPS somehow, do you have pieces of the repair kit around?
Yes, I have pieces of repair kit around.
Rhetorical question. I know he had some of them.
And Kevin, if you want to show, we'll show the pieces, and then if you want to show the slides, we could start on the slides on slide 63.
Okay.
But when we were in Don Pettit's garage, right?
Yeah. The offsite laboratory.
Offsite laboratory. Offsite laboratory. Thank you, John. This is going to be totally edited. But one of the problems with the original design for the repair using a plug or a patch, just like you would patch a tire, a hole in the wall, right? Was using the same material that the wing leading edge was made out of, right? The problem with the program patches, they were too thick and they were too stiff, and so they were causing very high temperatures and they were burning up. And because they were so stiff, you needed like 1,800 of them for you to be able to repair a piece anywhere on the wing. So imagine taking 1,800 of these. And so we went
trying to install those on orbit on an EVA. That doesn't sound very realistic.
Exactly. So I said we could do this better, and thankfully Kent Rominger allowed me. We went in Don Pettit's garage, and the Friends of Charlie Network, a fellow named Francis Schwind at CCAT in Texas, started sending us prototypes of the material in the designs we wanted him to make. Almost immediately, like within weeks.
Right.
And this was the same material that NASA wouldn't give us because it was so critical that they needed every bit of it. So we were getting material and we were experimenting with it. And we came up with a repair technique that basically you drill a hole.
I love that you just have this here we go. We drill a hole.
Well, I was prepared, but it's in my office. And this is the drill bit that Don Pettit and I and a fellow named Ron Penner and the team at Langley Research Center came up with to drill and tap any size hole. And then we had fasteners made out of carbon material, any size fastener for that hole that we could put a patch on. And because it was doubly curved and flexible, you can compress it. And instead of having 1,800 of these, we only needed 18 when we flew in space. So eventually I was selected to fly on this mission. I was doing this thinking I was never going to fly in space.
Knew. You were doing this for other people, to keep other astronauts safe, and it turned out to be you.
Of course. But anyway, So that's an interesting story because it talks about if you develop the right team and you give them the freedom and you
Yep.
don't control them by having program managers that weren't raised in a research culture,
Yep.
you
This
can
isn't
get things done.
this isn't like, okay, well, we initiated phase 3 of a feasibility study to see if you could make a patch of like some folks that were engineers got together and worked on the solution.
Yeah, let me explain something, right?
Okay.
After the Columbia tragedy, we could have picked anyone around the world. They would have helped us for free to help NASA solve this problem.
Right.
The good people that I reached out to in their organizations like Lockheed, ATK Thiokol, Boeing, the people that we reached out to sent us material, me and Don. I'm sure they didn't get approval for it, so I'm not going to mention their names.
That's fine.
Because they knew we had how to do this. We didn't have to go out with a contract, with look at proposals, select a contract. We would have never been able to do that. Kind of
Right.
like the way the people are trying to solve the Artemis problem right now.
Yeah, gotcha. We're jumping all over the map, but that sort of leads into a discussion, right, about the culture and about the way that you make an organization that can fix these things. And I've had the opportunity to read through a lot of your book. I didn't get through all of it yet. I'm definitely going to do that. I think the hacksaw story was in the book. I saw the hacksaw story somewhere, so I don't think you like leaked anything there. I'm pretty sure it was in there. You're good. But
Well,
you talk about in the beginning where NASA came from, right? And we get back into the NACA days, and we get into this organization that was made of engineers and scientists trying to figure out how flight works, right?
Yeah.
And this whole thing, it wasn't about making a product or making a program or anything like that. It was engineers and craftsmen that were just figuring out physics, basically. And that's what that organization was, right? When Shuttle started flying, or I guess when NACA turned into NASA, it sort of inherited that from the original NACA. They're engineers, they're craftsmen, they're doing things mostly. They're not managing big programs. Talk about that some for us.
If Kevin could bring up slide 102.
All right.
Okay. And I talk about this in my book because NASA was only research centers doing applied research. Okay, and it was established in 1915, 1917. The first center was NASA Langley. It was called the Langley Memorial Aeronautics Laboratory. And the whole purpose, when you look at the mission of NACA, was doing applied research to understand the physics of flight through the atmosphere and to transfer that knowledge to make our aerospace industry the best in the world. It's right out after World War I. U.S. didn't have any planes flying in World War I. And we wanted to have the best of the industry, aerospace industry. When we entered World War II, a lot of our success was based on the findings from the good researchers at Langley, Ames, and Lewis Research Center, it was called back then.
Okay.
And so one of the chapters in my book, I talk about this gradual slide of boiling a frog from a preeminent research organization into almost a production organization. The program got huge during Apollo, and I talk about how right after Apollo, we started working with hundreds of contractors around the country, Werner von Braun and other great researchers and engineers could no longer keep everything in-house. You know, the team at Marshall Space Flight Center was very similar to the research centers at NACA, and so they started to merge. But when it became too much that we had to start contracting things out, we could no longer take apart what people were building and understand it and test it to our satisfaction in the laboratory. And then we started flying as if we were a business, a research organization. People thought the shuttle was operational. It was always experimental. But we lost touch with the people at the research centers that had that knowledge. And so Johnson Space Flight Center slowly drifted away from its connections to Langley. And so when you have really critical problems, like when the tiles were flying off the space shuttle on the first ferry flight from California, to the East Coast for it to launch. Hundreds of pilots came off. They didn't have an independent review board. They had a real Tiger team, and these people had enough time and enough money, and it was led by a researcher, not a program manager, not a flight director, and they weren't just reviewing what someone else did. They did their own objective analysis and discovered why the tiles were coming off. And it's a great story. I have it in one of my papers, of lessons from Shuttle, the von Karman lecture I gave. And it was all because it was led by Paul Cooper from Langley, my boss, who was in the thermal structures branch, who led the thermal structures branch, or was a branch head in the thermal structures branch.
Yep.
He led that team, and he went through a process because it was a Tiger team, and it was led by a researcher where they were looking at multiple different analysis techniques, multiple different experimental techniques, and when they were transferring the data, transparency. So I have another slide where I talk about the difference between a research culture and a good engineering culture, and that's slide 8.
All right, Kevin will get that for us. But let me ask, right? It seems like you're advocating that an engineer should be in charge of running this team. And I think some people would say, well, an engineer isn't good at communicating and managing people. An engineer is good at engineering. Don't you need a specialized program manager with special skills to enable communication? I'm trying to come up with buzzwords here, right? Like, why could an engineer come up with a team that would make better solutions than somebody who's really good at running teams?
Because if you have a manager, and I would say not just any engineer, I would say a research-based engineer or someone who has had training. And so when we develop our program managers, and this is something I did when I was director of engineering, wanted to have a separate organization, and we needed to train the people that we raised as program managers. You just can't take a flight director or a program manager and make them a program manager. All right. They're trained to do how to operate the technology, how to look at every possible way it could fail and have a scripted solution when launch day comes. They don't have time to do analysis and test. They're not tolerant of failure. You know, failure is not an option. It wasn't really a real thing, Gene Kranz said, but there was no time for failure. They had to have everything on their script. And that's not the person you want to lead a research and development organization. So if you want to train real program managers, you have to retrain them. You can't just send them to an Apple class and they go out to Wallops Island and they take this class. The way I suggested training them was hands-on. You have a parallel program that's working side by side with real project on real critical issues, and you train them how to work with a team of researchers and engineers to solve problems. Then they will understand and they will gain that tolerance to be flexible and not have a directive style management because they're no longer worried about 8 minutes as a launch flight director, and they only have to make split-second decisions.
Right. I mean, would you say that it has something to do with what's the right way to say it that I would use, like a basis of knowledge? Like, do you need to have that basis of knowledge as an engineer so that you can really appreciate how this team should work? And you can't just take regular Joe Schmo who's really good at projects but knows nothing about space shuttles or TPS or systems or whatever. Train that person.
It won't work. I mean, you could try to train them, but they need more training. Right? And you don't know if they have the right skills. And so let me explain these systems. You have complicated systems, you have complex systems.
Sure.
Complicated systems are almost deterministic. You could predict how they're going to fail, how they're going to operate. When we start talking of space shuttles, nuclear reactors, power plants, Department of Defense, we're talking about complex systems. There's hundreds, if not, there's millions of pieces, hundreds of systems, dozens of subsystems, and these systems interact, these elements interact in complex, nonlinear ways, and the problem becomes so complex, and when it could become highly coupled, that very small changes could cause a failure, and you can't predict when the failure is going to happen. Right? And so I explained this in the second half of my book, the difference between complicated and complex systems. And the best we could do is identify when we see an anomaly that we can't understand. If you don't put the right team on that anomaly and understand the root cause, you will have successive failures. And so, for example, space shuttle foam coming off the ET tank, right? Every time they tried to look at it, they thought they understood how it performed. You fly again, another piece comes off. We're never able to predict how that foam would come off. These are complex problems. So when you look at something like ablation, that's even more complex.
Didn't that happen? I mean, so Columbia, we know Columbia, piece of foam came off the ET, hit the leading edge of the wing, caused the hole, and that's what caused the vehicle to be lost during reentry. Then you got on your space shuttle, and foam fell off the ET again. Did you know that it was still going to fall off? Did you say that it was still going to fall off? Like, let's talk a little. Look at this. Here's an image.
We actually have the video of this, right?
Yeah.
And so the program gets together, and they're all focused on developing flight rationale. Let's figure out how we could fly, keep the shuttle flying, meet schedule, meet budget. How do we do this? Flight rationale. They're around the table at a flight readiness review with about 300 people, maybe about 15 around the table, and they have to make a decision. The people conducted probabilistic risk assessment. I wrote a paper on this, on how bad it was, predicted that this foam would come off. You had a 1 in 10,000 chance that this PAL ramp would come off. Right. And so we have that video, Kevin, if you want to show that. It's a PAL ramp ET ascent, right? So we were told there's a 1 in 10,000 chance this is going to happen because the crew asked to take this piece of foam off. And they said, don't worry about it. You have a 1 in 10,000 chance. I wrote a paper on this, on why you shouldn't trust probabilistic risk assessment, or at least you should ask intelligent questions.
Okay.
And immediately after the SRB is jettisoned, 2 minutes into flight, right where that SRB is located, you're going to see a 3-foot section of a PAL ramp come off.
Right. So this is what we're seeing right now is your flight, right?
This is our flight. This is the camera. All right. Now look, right where that came off. That was the foam that came off. You saw it fly under the wing leading edge. Yeah. Right.
Look, Kevin's going to rewind it for us to that part.
What 1 in 10,000 chance
that's going to come off, and here's your 1 in 10,000 chance happening on the next flight.
Yeah. And so if that would have hit our wing leading edge, it would have hit with more energy than the bipod ramp that hit SDS 107.
And it's, I mean, I don't know if luck is the right terminology, but the way that thing came off and flew, it looks like it went under the wing and didn't actually impact the wing.
No, but if it hit the wing, we probably wouldn't be here. The other thing that the program told us and told the public was that we had a backup plan for this. Our backup plan was the astronauts. We were going to be sheltered on space station, and they would ready a new shuttle vehicle to come up and rescue us. And so you know what decision was made the day that the program managers saw that large piece of foam come off?
No more shuttles flying until they fix the foam.
The shuttle was grounded.
What I would have said.
But then
how are you going to use a shuttle to save somebody if you just grounded the shuttle because the shuttle you launched had a problem?
So think about this. If you're trying to create a story, and I call flight rationale a story, and it sounded like a good strategy on paper, right? But you have to think about, if the same exact failure happened on the next mission, were you going to risk another crew?
Right.
And I guarantee you, everyone in my office would have been jumping up and down to fly on that next shuttle, because that's what we sign up to do.
You sign up to do, sure.
Yeah.
And folks, let me just make sure that everybody's on the same page here. The video we were just watching was the return to flight, right?
Yes.
The Columbia had a piece of foam come off and hit the wing and cause the problem. And then the next flight, they worked on it for 900 days. They looked through all this stuff. They do all this testing. In the next launch, 114, that you were aboard, Charlie, another piece of foam comes off. And just the dynamics of how that airflow worked caused that piece of foam to not hit the wing, and therefore not, as far as y'all know, not cause a problem, right?
Right. And the ability to predict where that foam is going is very difficult, if not impossible, because you have interacting shocks between the two vehicles, yada, yada, yada.
Yep.
Okay, but remember...
I mean, what's the size and shape of it, too? Like, okay, some foam came off, but what's the size? What's the shape? How much drag? What are the aerodynamic properties? Like, you can't predict exactly how the foam's going to fail, so you can't predict what the size and shape of the foam is going to be, so you can't predict where the heck it's going to end up.
That's all in a paper I wrote for the AIAA called "Failure is Not an Option."
Yeah,
that was the title I gave. But you have to remember, after the foam came off for Columbia,
right?
They took that bipod foam off the vehicle.
They actually took it off.
They took it off, and so if somebody conducted probabilistic risk assessment and said, you know what, probability of you getting hit with foam that isn't there is 1, I would believe that calculation.
Right.
But after
the best part is no part. Like if the foam isn't there, it can't fall off and hit you and cause a problem. So just take the foam off.
Exactly.
If you don't need it.
We asked them to take off the power ramp. They didn't do it. After it came off on our vehicle, they spent another year, figured out they could take it off for the next shuttle mission.
Well,
right?
what's it for? Like that piece of foam, the PAL ramp, what's that even for?
That extra foam was put there because they were being extra conservative. It was protecting it from the heat. It was also going to help make the flow throughout that a little bit less turbulent, if you will. Okay.
So they thought they were being extra conservative, but it also increased the complexity and the chance that, well, there's more foam now that could come off, right? It's a weight balance.
Exactly. Okay. It was so they take the power ramp off. Now we fast forward to the next flight. I'm no longer an astronaut. I'm the director of engineering. Right. And so if we could go to, let me see where those slides are.
Charlie, while you look,
those slides are.
Let me tell the audience, Charlie has these presentations, and we're structuring this as like a free flow conversation. He's got all of you do talks, you've written papers, you know all this stuff, and here I am asking random questions, and we're sort of winding all over, messing with the normal flow. But I
like it better that way. So, Kevin, if you go to slide 33.
All right. We'll get slide 33 from Kevin here real quick.
Okay, so now I'm director of engineering.
Right.
For 8 months, I'm in charge of an engineering directorate. Mike Griffin asked me to do this before I flew in space.
Okay.
And I said, I really don't want to be the director of engineering. I want to go back to Langley and be a researcher.
Right.
And he said, no, I want you to be the director of engineering. We need to change the culture. We need to make it technically excellent. He knew there were issues with JSC engineering.
Right.
And I said, okay, I'll do this if you don't tie both hands behind my back. I'll go in the ring if you don't tie both hands behind my back. And he said, don't worry, I got your back. And so as we were preparing to go to, if you back up, let me see, go to slide 30, Kevin. I'm sorry. If you go back.
The slide is like, I was there. There's me. I'm circled. And then Mike Griffin's there. Like,
Okay, we're going to come back to that, right? We're going to come back to that. And so I want you to see the next slide, Kevin. Well, the ice frost ramps, you can see it. It's those 3 blocks on those cables right above that. That's the ice frost ramp.
Okay.
And we in the engineering directorate made the decision that we weren't safe to fly unless we removed these ice frost ramps.
Right.
We briefed our director of engineering. I'm not director of engineering. I was the center director, Mike Coates, and we said this is our recommendation. Now, fast forward to the next scene, 33.
Was it just the PAL ramps, or were there more things? It's like, hey, there's a bunch of stuff on here you don't really need.
There was foam coming off the entire tank, and no one could predict where it was coming. But these were the next 3 big pieces, more than 3, that were coming off, right? And so we said there's no reason for those to be there. We should take them off for the next flight, because when we made the calculations, it was probable that this was going to come off and could be a serious problem.
Right.
So that was our recommendation to our center director. Now fast forward to to slide 33, the day of the flight readiness review.
Right.
I tried to talk to my center director, and he didn't want to meet with me to make sure he knew that we weren't ready for this. But when it came around the table and they asked him, and he's one of the signees for the certification of flight readiness.
Right.
Is JSC ready to fly? And Mike said, JSC is go for launch. And I'm sitting there in this room with my engineers behind me, and I'm just teaching them how to change the culture and how to be responsible and to stand up. And after I stood up, the next person to stand up was Chris Scalise, NASA's chief engineer.
Wait,
He
time out.
said-
So they said JSE is go for flight, and then you stood up like,
and had to say, and counter my boss's recommendation and say, we are not ready to fly.
that doesn't win a lot of friends.
No, it didn't. And if you go back to that picture, the next person to stand up
Yeah.
was Chris Scalise was the chief engineer.
So that's
He-
the context of the picture. You're standing up in this review. This
Yes.
isn't just a random picture of a room showing that you were there.
No.
Really?
This is the day. This is the day. So look at those people's faces in the audience looking at me.
In the
Counter-
background, yeah.
Counteracting by the decision by my boss that we would go for launch. Now, in a psychologically safe environment, what I told my engineers was if I stand up and there's 300 people in the room and I make a mistake, you have to stand up and tell me. And if you don't, then you will be punished. That's psychological safety.
Okay.
All right. So I stand up, the chief engineer from NASA headquarters stands up and says, we shouldn't fly. An astronaut, Brian O'Connor, who is the head of safety and mission assurance, says we're not safe to fly.
Okay.
It's 3 people. And Mike Griffin says he will accept the risk. And so if you go to the next slide, Kevin, this was the first time in the history of Space Shuttle where we had 2 items in the upper red box of the likelihood and severity matrix,
Right.
the risk matrix. The likelihood of ice frost ramps coming off and the severity would be catastrophic.
Catastrophic. Y'all see the graph there, like the bottom, I guess that'd be the x-axis. It's marginal, not a huge deal, critical or catastrophic. Catastrophic, of course, is a piece of foam hits a part of the TPS that then cause a failure during reentry or something like that, right?
That's
and then
right.
the Y column is the likelihood. How probable is this of happening? Is it really likely to happen? You knew foam was falling off left and right, so probable, right?
They were predicting, the same people that do the PRA were predicting 1 in 75 or 1 in 100, but we know the PRA is inaccurate. So now, if you show video IFR release, what do you think happens on this mission?
I'm going to guess that foam fell off.
Yeah. And so headquarters asked me to be in mission control for STS-121, right?
Right.
And you saw it came off, but you just missed it. Pieces of ice force ramp came off, and you can't really tell where they went, but they went above and below the wing leading edge.
Yep.
And so now
They split the difference, but again, the same sort of thing.
Exactly. The same sort of thing. And so now those people made a bad decision, right? But they don't know if it damaged the wing and if it damaged it critically. So
that's a huge part of it. Okay. You didn't, sorry, Charlie, I apologize. I keep jumping in, but you know that it's likely that foam's going to fall off, and then you're sort of running the roulette. Well, what's the foam going to hit? How big is the foam going to be? Is it going to make a hole that's big enough to worry about? Because you can't model all of these things perfectly, right?
Yeah. And so remember, this is probability theory, right? And in these cases, it was garbage, right? Because when you think about it, 1 in 10,000 chance, and it happened. This is 1 in 100 chance. They're not really good at predicting when things will happen. I mean, those odds are pretty good that it's not going to happen, right?
I'd expect 5,000 shuttle flights on a 1 in 10,000 chance before I may start to get to where I see one. And it's one shuttle flight where we see it. Or you know, I'm making up numbers, right? I haven't written these papers.
So now you fast forward to the next slide, Kevin, slide 35. And what do you think those 2 people that stood up and said we shouldn't fly, because they have to sign the certificate of flight readiness. Right. Those same 2 people on slide 35, look at what they crossed out on what the wording is on the statement for flight readiness. I concur with proceeding with this mission. They cross it out, Chris Scalise, Brian O'Connor.
Is this
and they
before
put-
flight?
No, this is before
This is
flight.
flight readiness review for STS-24.
Yeah.
Before flight,
120.
they crossed it out?
You see it right there, right? And they write in this caveat, oh, but this is the reason I remain no-go, but I'm not going to appeal the decision because of CSCS. CSCS was the ISS safe haven, which wasn't there. Cross that out, right? That wasn't an option. Then you go down to the next one, and the reason for not appealing this decision was because he accepts Mike Griffin's reasoning for accepting flight rationale.
Okay. Well, maybe we can zoom in on the next one too. And the safe haven, the CSCS safe haven thing, the shuttle was supposed to be, it wasn't as realistic as we thought it was. We have STS, what was it, 300, 400? I know it had hundreds, right? Shuttle on the pad, ready to rescue astronauts, that sort of thing that we all think is so cool.
And let me say something. Being able to ready a shuttle to fly in 30 days, having it on the pad, even if it's on the pad and having it ready to fly in 30 days, we know what the launch rate is, what the scrub rate is. That's pretty iffy. But anyway.
No kidding.
Neither here nor there. See, people don't know these stories. People don't understand this, right? They haven't heard these stories. And, the reason why I wrote the book, right, John, is because unless I tell that first half of the book that explains how ugly the situation is at NASA, people won't believe it. People believe NASA is this shining organization on a hill, and Boeing could screw up, and BP could screw up, and nuclear facilities could screw up, but not NASA, right? If I didn't explain that and explain that these decisions were based on a toxic culture, and I go into excruciating detail, and if you look at my book, I have endorsements from the great people that did the sociology and behavioral science. Amy Edmondson, Michael Roberto interviewed these people, spent 15 years understanding the causes of culture. So when people say they understand culture, you have to read, if you read the Challenger launch decision 6 times like I did, and talk to these people and spend 15 years, because I was embedded in this organization. So I understood the difference between culture, and it's not just one culture. What I explain in the book is there's multiple cultures, and Diane Vaughan says it could be as many as you have working groups. So you can have thousands of subcultures. So the teams that were making these very bad decisions, the O-ring team and the leading edge structural subsystem problem resolution team, the LES's PRT that was supposed to be the experts on wing leading edges, if you have dysfunction in those two teams like we had, presenting a story which isn't true, isn't based on sound engineering, sound research, critical things can happen. And it's almost impossible to do that. So the second half of my book was what I was working on with people outside of NASA for 15, 13 years after I was reassigned. People like the chief learning scientist at Boeing, Mike Ritchie, people from Finland, Jana Hatela, and others, to develop the technology to be able to put together these high-performing teams quickly, and then to give them access to the information, and then to monitor those teams to make sure they're behaving the way you think they are, so that we could determine the weak signals, whether they're technical weak signals, because we see foam coming off. You should start attacking that the first flight of Shuttle. You should have a team on there understanding that, to understand how critical it really is, so that you prevent those accidents from happening. So
it is a balance. We have to make sure it's a balance. Okay, somebody thought the foam needed to be there for whatever reason, insulation, aerodynamics, whatever, right? And then the risk, because you've added that foam there, is now that foam could come off. So you have to have somebody that's intelligent enough to sit there and weigh the benefits from that part, from the risk of that part, right?
Right. But when you see it come off, and it came off on the first or the fourth shuttle flight, I think, was when we had a large piece of a bipod ramp come off. People, it was a failure of imagination. the people at Johnson Space Center, the people working on the shuttle program did not say, what if that
Right.
piece of foam hit something? Because we had the researchers that solved this problem when I initiated the team that put these researchers together, because I knew them, friends of Charlie, and we could talk about that, from Glenn, from Langley. We brought great people from Boeing, Philadelphia, that were researchers looking at impact and ballistic impacts. We solved this problem in 3 months. So imagine we could have had this technology in place way before the crew of STS-107 ever flew, that we would have known immediately that was a critical problem. And we would have...
Why did it break down? So there's teams that are working on this. We know that foam is a problem. We know that TPS damage is a problem. What, in your estimation, because I know we're sort of looking at it with a different lens here, what was the problem? If this solution existed, why was it not applied to the shuttle? Was it like organizational inertia? Was it lack of communication? Because
we lost at Johnson Space Center, lost its research edge. Right? They
what does
lost
that mean?
They were no longer research engineers. They were no longer researchers. Now these people aren't conducting real research like we did at Langley to get the shuttles operational. This what's called sustaining engineers. All they're doing is looking over the shoulder of people, the contractors, and most of the time they're not even doing independent analysis on their own computers with their own programs to check what's happening.
Right.
Okay? So they don't even know. See, the way we operate, and I talk about a research network of teams, you have to pull the right people together to create this team, to make the magic happen. Johnson Space Flight Center, even the NASA Engineering Safety Center, failed miserably in being able to put the right teams together. And I talk about that in chapter 4, when they were trying to discover problems with the panel on my wing leading edge, panel 8R, the 8R anomaly. It took me a year to convince my own people, because now, after I was reassigned, after I stood up at the FRR for 121, I was reassigned to work with Ralph Rowe under him in the NASA Engineering and Safety Center. Well, I'm sitting at my desk. I see an obscure email from people in the LESS-PRT with an attachment. I open up the attachment and I see major damage on my wing leading edge after we landed, that they were inspecting and trying to figure out large damage to the coating that came off easily when they took that panel off the vehicle. And NASA didn't think that was a systemic problem. The LESS-PRT didn't think it was a systemic problem. They didn't stop flying the vehicle. And if you see pictures of this, and you could see it on slide 39.
All right. Okay, we'll get slide 39 in just a second here. I'm like looking all over the map. Here, there we go.
Yeah.
This is, you said your shuttle. Like, when you say your shuttle, you mean the shuttle that you flew on.
Shuttle Discovery that I flew on. They noticed an anomaly. If you go to slide 38, Kevin, you'll see we developed IR technology at NASA Langley in order to inspect these panels in situ. We inspected them before we flew. We didn't see any anomalies. We come back from flight. You see on the upper left, that red circle. They see something that doesn't look right. Right? Now you go back to the other panel. When they start inspecting that, they put it on a bench, take it off the vehicle, and the technician comes with a little dental pick and just touches it, and large pieces of silicon carbide coating come off. So if you look at slide 39, the total amount of damage, you look at the underneath, you look at the gaps under the coating. This coating is only about 40 mils thick. If you lose a thumbnail-sized piece of this coating, your wing burns up when you re-enter the atmosphere, when you enter the Earth's atmosphere.
What are we, like, this thing that we're looking here, like, in context, where is this at? Is this on the leading edge of the wing? I don't even really understand where this is.
Yeah. So if you go to slide 41, if you go to slide 41,
it'll take us just a second, but Okay.
You notice in the left-hand figure, you have 22 RCC, reinforced carbon-carbon, wing leading edge panels. And you notice those red areas
Uh-huh.
on the tip and also closer into the fuselage structure?
Yep.
That's where the bow shock interacts with the shock of the wing leading edge. And so you get shock interference patterns happen and cause extra heating. This damage was in the worst possible location on the wing leading edge. And so immediately it would make you think this is a systemic problem. It has something to do with the number of flights you fly,
Yep.
how often you inspect it. But the team on the ground that did not stand up and say, there was a problem with the shuttle foam on SDS-107. That same LESS PRT and the damage assessment team that thought the wing leading edge was strong enough and could survive that hit stood up and said, this is not a systemic problem immediately, right?
Wow.
And so I started diving into this because I didn't believe them. I started making noise.
Yeah.
And then what happened was I was canceled. My own organization, which was the safety organization, I got taken off email list. I had to prove that this was a problem to my organization.
Okay.
I became a dissenting opinion, right? I was no longer on the safety team anymore. I was a dissenting person.
Right.
And they were preventing me from getting the information I needed to show this was a critical problem. Are you following me?
I do.
And, and so Charlie Camarda is trying to cause a commotion to get these people to realize this is a problem. I'm not given any support as an engineer to prove that what the program is telling you is a lie. So I have to do this all by myself, and they're preventing me from getting information to the point where I had to file a Freedom of Information Act request to get information.
Did you work at NASA?
I was working at NASA. I was in the safety center. I was a deputy in the premier safety organization, the NESC.
Okay.
Okay.
And in order to get the information, you had to file a FOIA request?
And of course it didn't come. It came too late. And but yet I still had constructed enough of a technical argument.
Yeah.
That I wrote a 117-page dissenting opinion. I gave it to the second in command in the NESC and to other key leaders in my own safety organization, and they either didn't read it, and when I asked them to please read it, they said, Charlie, we're not supposed to edit your paper.
Okay.
You know, we are struggling to have to provide flight rationale to keep the shuttle flying. So this is what the safety organization is saying. They're basically saying, listen, we don't have time to look at these dissenting opinions and run to ground these critical issues. We are helping the program office create and provide flight rationale. So it's no longer an objective organization that's looking over the safety of NASA.
Right.
At one point, I suggested to the head of the NESC, I said, we need a totally independent review of this ADAR anomaly. Let's go outside the agency. I even suggested people inside the agency, people I knew that I trusted, friends of Charlie, like Corky Clinton at Marshall Space Flight Center. I also suggested if they really wanted an independent review, you should do something like the Aerospace Corporation that helps the Air Force decide whether or not they're safe to fly. The NESC is not an independent organization. The teams they create are not independent. The teams that NASA is putting together right now, if you look at the makeup of the people on the teams, I question their independence.
Yeah. Charlie, like, how do we keep flying, though? Because I like seeing things fly. I want it to happen safely, but there has to be a balance. You have to still be able to make progress. You can't just shut everything down constantly due to safety issues. So what are we doing wrong? How do we continue flying humans in space, but we make sure we do it safely? Talk to us about that.
I'll tell you, it's very simple. You know, in all these cases, if it's risky to fly with ice frost ramps, how much, I mean, we waited a year to take off the power ramp. We
Okay.
waited a year and we waited 2.5 years to figure out the cause of Columbia and take off the bipod ramp. We could have taken off those ice frost ramps quickly. It would have caused a little bit of a schedule hit, a
Right.
little bit of budget cost, but it's worth it. So you talk about the 8R anomaly. If you saw how bad that was, when we did the analysis, we found out that there were 12 panels on all three, spread across all three vehicles,
Right.
that had the same criticality of that indication. And I want you to show this. You need to see this.
We'll grab it. Just say it out loud. We can
slide.
find it.
We are going to, because this will make your hair stand up.
I do, Charlie. While you look, I want to talk to the viewers a
Okay.
little bit here. We're not saying to shut everything down. There are ways that we can proceed and try to do these things, right? We're not saying that it's not ever safe to fly, so we shouldn't do it. We just need some ways to do it more safely. We're looking, I think, for... Yeah, okay, the video's not frozen. We're good. We're looking for this other slide we're going to go through. But, folks, I'm reading your questions. Right now, we're very much in let Charlie cook mode, the way to say it. I want to listen. I want to hear from Charlie and what he's got to say about this stuff. There's so much commentary in the chat. So thank you, A, for keeping it respectful. There's a lot of opinions over there. But B, we're going to talk a little bit about other things that are happening contemporarily. What's going on with Orion, right? What's up with SLS? The SpaceX has some TPS on it. What's about Starship? I see a lot of people asking questions like this, Charlie, but did you find that slide you wanted?
Yeah. It's slide 22.
Okay, slide 22.
Slide
again,
22.
We're jumping all over here, but I'm okay with it.
But
I think the viewers are okay with it.
It's fitting in perfect the way you're asking the questions, John, but it's so that I don't have to give this boring pitch, right? So you saw that the damage, right? And the IR camera detects that there's an anomaly.
Okay.
And it was done by an amazing person named Bill Winfrey at NASA Langley, one of the NDE guys. And so it became the Winfrey. The level of damage became a Winfrey. So if you look on the horizontal axis, the IR indication is in Winfreys.
Okay.
Right?
I don't even know what a Winfrey is, Charlie. But it's
I don't even know what it's based on. But these people developed the NDE techniques. This is the difference between researchers doing NDE and NDE people. Okay, and it's amazing that the shuttle flew for 30 years, and the only means that they had to determine the integrity of the coating was someone was supposed to go in these areas and press that carbon-carbon leading edge with their finger.
That was the test.
That was the test. There was no criteria. There was no criteria because it obviously passed that test, and we came back and you saw what happened. There was no criteria. So I told people in the NESC, we need to have a real structural criteria. And when they went out and actually did this, you look at that's the tensile strength of that coating as a function of the IR indication in Winfrey's. And when it hits 0.2, the strength of that goes to almost zero, right? It goes straight down.
Ah, that's what it's showing here. Okay.
And so what I'm telling you is shuttle managers flew the space shuttle 8 times, knowing that there was 12 panels that had this level of an anomaly. Now, you asked me, what would I do?
Yeah.
Well, we have spares.
I want some solutions. Like, I want solutions going forward.
I'll tell you a real simple solution. If you have a problem with your tire, what do? Do you put your family in a car and drive cross country, or do you change the tire?
I'd change the tire. I'd make sure that I knew I could safely hop in the car.
We have spare RCC panels. What that meant was, just like we took off the bipod foam, PAL ramp, ice frost ramps, you take off those panels. Why fly with those panels? You mean
replace them with another panel that doesn't have the anomaly. It's not that the panel's not required. It's that you have another part that doesn't have the problem.
Right. Thanks for clearing that up.
I got you.
Yeah.
I mean, I'm putting myself in the audience's shoe here because I am not the engineering expert. Like, I'm trying to understand these things, and I hope somebody's not over here like, oh, you didn't even know what a Winfrey is. He can't talk about this. It's like, I'm the public. I want to understand. Like, I want to have confidence that when NASA's putting astronauts on our space shuttles or capsules or whatever, They're coming
Let
home.
me tell you something. I don't know what a Winfrey is, but the reason why I trust Bill Winfrey, and he's a friend of Charlie, and he's in that notebook
Yeah.
that I took to space, was because the people at the Cape, they're all good engineers, but they're not researchers.
Okay.
They do these same inspections. They do not see this. They talk to Bill Winfrey. He has them tweak the dials on the same machines,
Right.
and they could see the damage.
Ah.
Bill Winfrey, the difference between a research engineer is Bill Winfrey and his team designed the algorithms to detect that damage, to do flash thermography. The temperature goes down, it goes
Okay.
in. You look at the transient response to that temperature, and it tells you if there's something below the surface that you can't see.
It's almost like I don't know. I would be totally making things up, but you're hitting the surface with the scanner. Let's use that for lack of a better term, and it reacts differently. So, how, as an organization, do you know that Winfrey's idea makes sense, but Joe Bob's idea? I don't know who Joe Bob is. Like, how do you distill that down to the people who know how to get stuff done, and you don't have a bunch of noise in your signal?
I talk about this, and I talked to a person in the Netherlands who wrote his dissertation on this.
Right.
And it's all about the know-who with the know-how. You know the person, right? You know who to go to that has the expertise.
Right.
You know how, but you know the person. You know how that person was raised, how they were mentored. You understand the integrity and the rigor and the fact that they were raised in a psychologically safe environment. If there was a problem, they would raise their hand.
What does that mean?
Psychological safety.
Yeah,
Psychological safety.
Times.
All right. And Amy Edmondson wrote a book about this. It's called The Fearless Organization. You should definitely get it.
Okay.
I've spoken to Amy Edmondson. She's endorsed my book. Psychological safety means you are free to take interpersonal risks in your organization without fear of recrimination, retaliation, without career suicide. Not only that, but your boss has your back. And that's what I told the people in my engineering directorate, that if they have a problem and they do not have the courage to come forward, they come to me. All right? I'll take the heat. I'll get fired. That's the difference between a researcher that grew up in a culture where we have these tough discussions. I mean, people at Ames Research Center, we fought with them like mad because they were designing ceramic TPS, shuttle tiles, ablators. We were looking at more durable, high temperature materials, what do you call it? Metallic materials. And it's what's called competitive collaboration. My good friend Bart Bartholomew, that ran the National Aerospace Plane Program, he wrote a good book, The Sky Is Not the Limit. And everyone should get that book because he ran a program, the National Aerospace Plane Program. I was I was the head of structures and materials for the TechMat program for briefly working with Bart. Amazing researcher, PhD engineering, electrical engineering, and he ran the entire program. And the way he ran it and the style of management, he knew how to connect the right people together, just like we did. And so we had a very good program. But
do you see any organizations these days that are doing that sort of thing? Like NASA needs to find its way back. Are there other organizations that you're aware of that are doing things right?
I would say that.
Put you on the spot.
No, yeah, you can put me on the spot. I don't care. But I have not had insight into what Elon Musk and his team are doing at SpaceX. I've doubted a lot of things that they would be able to do. He's proven me wrong.
Right.
But I would say they're doing a lot of what I see right, but I'm not sure if he has the right culture. I don't know because I don't know firsthand. I don't have insight. I would love to talk to him. I know he's doing things a heck of a lot better than NASA. I don't like the fact that he's failing big. I mean, but he's flying rockets cheaply so he could fail big.
Yep, and no people aboard, right? When our new technology, not new technology, Shuttle could have flown uncrewed, right?
Right, absolutely. It could have, just like Moran did. We just had to make a couple of modifications. And as a matter of fact, that's a good point. In the strategy to return to fly again, one of the recommendations I made to my the head of my office, Kent Romiger, and he kind of
Yep.
looked at me like I was crazy. I said, we should have, before we fly again, we should have an autonomous return capability, undock and auto land. And he
Right.
thought I was crazy. But
Right.
you know that when we flew in space, we had procedures so that we could have made a couple of rewirings of the orbiter. People on the ground would have been able to take down the landing gear, take out the air data probes, and we could have landed that vehicle safely someplace. And the reason for doing that, in my mind, because you decouple the crew from making that decision. The crew doesn't have to say, we want to fly back, because they will, not to lose the program. They could safely say, now we'll just fly the vehicle back. We won't lose the entire space program. Why put them in the hot seat?
We almost get back to making decisions for yourself, like, I'm the astronaut, I'm going to risk this, versus we don't have to risk that, right? You talked about that at the very beginning. So this is, we've got 10 minutes left, by the way.
Oh my God.
I'm curious about this. I've seen this question come up over and over again. I would probably say that some of the results we see coming out of SpaceX may indicate that maybe they're doing things right, because we're getting things done really quickly and cheaply in results, and they're not always success, but it's always forward progress, right? They're moving the ball down the line. So maybe that speaks to what culture is sort of like driving this. I've heard engineer in charge, right? Like the responsible engineer. I've heard that in terms of
engineer in charge
stuff. Yeah.
Engineer in charge is a term that came out when you look at the SP, that's the historical report on NASA Langley Research Center.
Yep.
They use the term engineer in charge. And when you had a Werner von Braun at Marshall Space Flight Center, he was an engineer in charge. He had it all.
Yep.
Okay. He had everything.
So we see some of this. I'm going to ask once again on the spot. Have you looked at the thermal protection system that they're using on Starship? What do you think of the live HD video of the plasma forming around the TPS coming back from space on Starship?
Okay.
You got a chance to see some of that?
Yes, I did. Yes, I did. And so I'll tell you, this is why Elon Musk, he made a believer out of me.
Okay.
When I saw dozens, if not hundreds of those TPS panels coming off the first time he flew, and then
like confetti.
It wasn't able to re-enter, right? I said, there's no way, no how this guy is going to solve this problem on the next flight. It looks like he did. And I don't know how he did it, but he did. But the other thing I heard, and I don't know firsthand, is underneath, he has ablative material.
Yep, there's new layers.
Protecting the shell of that vehicle. And so that's beautiful, right? And that's what a good engineer, like a good engineer and a good engineering designer, Petrosky, from Duke University, you obviate failure. You assume something's going to fail, but you obviate that failure by having a backup. And if a tile comes off, he will survive safe. And I commend him for that. We forgot how to be real engineers. We forgot how to fail, and we forgot how to design robust vehicles. And so that's the issue I have with the Artemis heat shield right now. Right now, you have a single point failure, and people are trying to convince you that they have the analytical capability to predict how it's going to come off. And I do not believe it. And they will not show the evidence. They will not show the data. They wouldn't let me be on any teams. They wouldn't let me form my own team because I wanted to help them. I could have helped them 2 years ago.
To be clear, you don't work for NASA anymore right now, correct?
No.
Let's just make that clear to the audience. Yeah. You just said robust designs, right? Did you see the footage of the burn through on the flap? Where there's plasma coming through the flap and molten metal splattering against the camera, and the thing is still under control and survives for certain values to survive.
Because he had stainless steel. But notice the other thing you saw, John, when you look at mission control.
I want to know what you saw.
At mission control at SpaceX, people are cheering. He's creating a culture where it's okay to fail instead of failure is not an option.
Right.
And I'm hoping that he's creating the right culture, but it's okay. So people could speak up when they fail. People aren't afraid to speak up when failures happen.
I think program wise, we see that SpaceX is not afraid to fail, and they let us see it a lot of the times, like the starship blowing up or.
But Elon, if you're listening, I think you need a little help with TPS, and I could help you pull together a team. I don't want to get paid, but I can tell you, yeah, I know you got a lot of work on your hands, but I think he needs help in the TPS area.
I just want to sit down with you, Charlie, and we'll just watch some of these videos over and just pick your brain about what you think about what you're seeing. Like you can see it on the screen right now, but SpaceX is getting this real, engineering footage back in ways we haven't had before.
He is making engineering exciting instead of hiding the information like NASA is doing with Artemis.
I think a lot of us feel that way.
They knew exactly how critical that ablation was. They hid it from the public, would not show a photograph until we basically shamed them into doing it by me continually blasting them on LinkedIn and other places. Show us the pictures, show us the pictures. The Inspector General finally put out the report and they had to come clean.
Why? So why do they wait so long? I get, okay, we want to make sure the final report is done and then it takes them forever to do. And correct me if I'm wrong, please. But even during Columbia,
Howard, listen.
Go ahead.
Hopefully, look at the list of people that signed up, or any of those program managers on the list. Please ask them to go in the chat box and make a statement so that we can get you live here. Because Howard Hughes' first statement to the press was, it ablated differently, but we still have a lot of margin. Anyone who saw the actual pictures, and we could go to the actual picture, right?
That's the bottom shot of of the Orion capsule.
If we do slide 13, right?
Okay, we have a slide. Cool.
Okay, yeah, we got a slide for everything. So believe me,
you've done your homework on this.
I have encouraged NASA managers to be on this video chat. If I say something wrong, please correct me.
Yeah.
If I said dissenting opinion and it wasn't a formal dissenting opinion, please say something, but at least admit to the people you never asked them the question, or they weren't going to have a dissenting opinion. Howard Hughes' first statements to the press on March 8th, about 3 months after they recovered the vehicle, is that some of the charred material ablated away differently than our computer models predicted. A significant amount of margin was left.
Right.
He doesn't believe it reached the limits. He doesn't believe. But anyone in their right mind that knows anything about ablation knows this is not ablation, right? This is a totally different failure mode.
Yeah, this isn't how it's supposed to look.
And I think the next thing you heard was small pieces. When the OIG Inspector General report, Office of Inspector General report came out, 100 pieces, inches in dimension, almost an inch thick, came off this vehicle. And then they want you to believe in 17 months of them doing this analysis. If you go to slide 11, right?
Yeah. And I'm Charlie, I'm going to try to get some viewer questions here. I've been asking viewer questions as we go.
Let's go. Let's ask. What? This shows you the timeline, right? This shows you the timeline. Anyone in their right mind, and believe me, there are good TPS engineers that are almost my age at Ames Research Center that said this was crazy, put me on this team. They were never called to be on this team, right? This IRB. So they knew this for 17 months before they even instituted an IRB. But the IRB was toothless. I mean, they weren't given any money. They didn't select, in my opinion, the right people, and they didn't have people that did their own independent analysis. All they were doing was looking at what they were force-fed, and I've already told you the stories that some of these teams create to present flight rationale. An engineer tells you what they know and and the tools they used, what they predicted. A research engineer will tell you what he or she doesn't know and what's wrong with the tools, the limits of the tools you're using, because they're the people that develop those tools. That's the difference between a research engineer and an engineer. But if you put that slide back up, the one thing I wanted to stress on that slide 11 was that they would have had 2 years to put together a good team, a real team, and solve this problem. And a real Tiger team would be looking at multiple options. Instead, somewhere along the line, they made the decision to change the heat shield. After EFT1, which was an Apollo heat shield with ablative material in the honeycomb, because those engineers were a little bit smarter, because they also recognized that block Avcoat could come away in large pieces.
Right.
The program office made the decision to change the heat shield.
Okay.
Now, the reasons for doing it
after the first test flight.
After the first test flight, which came back fine, didn't go around the moon, slightly less heating.
Not the same energies. Yeah.
Show us the data that caused you to make that decision. Was it a technical decision that was a safety concern, or was it a money and schedule decision? And show me the names of the people that made that decision and what they based that decision on.
Yeah.
Because now they are looking at one idea, and they're only looking at that one idea and trying to create flight rationale, substitute flight rationale for story, narrative, to convince you, the public that doesn't know much about this, why we're safe to fly. But, oh, by the way, we're not letting anyone else see that data except these few people that we have on these teams that, oh, by the way, are made up of a lot of same people that didn't raise their hand when they made bad decisions in the past.
Why wouldn't NASA let us see that stuff? And let me come up with some guesses real quick. If I were to look at that data, maybe I wouldn't be qualified. NASA shouldn't spend their time listening to me, right? But there are qualified people who can review this data. Why wouldn't they show it to us?
You could look at that timeline. You could tell when I went nonlinear and started reaching out to Bill Nelson, when I knew they were. I predicted the path that they were going to take, and I put it as the last two sentences in the epilogue of my book, before they came clean about how serious this problem was, that they were going to go down the path they went down just now. They were going to fly as is because they kicked the can down the road, raised the production pressure. So now the heat is on for these teams to come up with a solution. And since they only reward people that come up with flight rationale, and not the people like me and Rodney Rocha that raise their hand and call them out with problems.
It's like not non-flight rationale, safety rationale.
And plus, there's a double standard. I have to go out of my way and have double the evidence and the rigor in my analysis to prove we're not safe to fly, instead of them having to prove that they're safe to fly. So the system is totally rigged. That's why I wrote the article in the New York Post, The Culture's Broken. And the reason why we're not going to solve this problem, and if Jared Isaacman is listening, it takes a sociologist, a behavioral scientist, someone skilled in organizational behavior to solve this problem. And so that's what I had to do as director of engineering. I had to create a research culture, but I also had to make a psychologically safe environment and change the culture. So I had to solve both problems. You can't solve just one, or the system will still be broken. Anyway, let's get questions.
Well, I've been asking a lot of questions here, like a lot of folks, because Starship is such a big thing that we cover and there's so much interest in it. We talked a little bit about a lot of questions that came through on your thoughts on the TPS system, the ATM machine, the TPS that you see being used on Starship. And we've talked about that a little bit. You said you felt like you were maybe proven wrong a little bit because you saw tiles coming off. I said like confetti. And then the next flight, they stuck better. And even then you see it surviving reentry with tiles missing. Let's talk a little bit more about that. People really want to know what you think.
Well, plus he has a backup. He has a redundant system.
Right.
So it's a little bit safer. And so I'd love to see the details. I would love to see the thermal stress analysis, the vibration test. He's doing great things.
Okay.
The issue he has to solve now is why he's having that heating in the gap of those fins that's going to overheat it's overheating the metal structure. It survives, but it won't be reusable, right?
Well, so the new version that's flying, the Block 2 starships are actually moving some of the forward flaps back around the body so that they don't get that same flow dynamics right on the hinge. They've moved the hinges, it's a big circle, right? And they've moved the hinges on the forward flaps up around the I want to do a show with you, Charlie, where we just look at Starship.
Hey, have Elon Musk let me and you sign an NDA and let us go chat with his people. I would love to know how he's doing it.
We could probably do a lot of analysis just on stuff we can see publicly. I'd need to send you some of this because I'd love to pick your brain up.
Yeah.
Not this show. That's a different show. They need to solve how they're getting that through the beginning. We think we've seen some things they're already solving, how they get that flow through the hinge. Shuttle had a big hinge on it. It had the body flap at the aft, and there was never really that, was there?
Oh, geez, what's the name of that person? I was going to give you the exact name of the person that was doing the seals for NASA, that did an amazing job for high temperature seals for the National Aerospace Plane. Let me see if he's on my list of friends of Charlie that I took into space.
The Friends of Charlie has somebody for that.
Oh my God! Oh yeah, he was from Glenn Research Center.
There you go.
And I know he has to be on here. Wait a minute, I have everything in alphabetical order, but I'm trying to figure out what his name is. Anyway, if he's listening, please put your name in the chat box so I could give you credit. That's the person Elon Musk has to talk to. But anyway.
I've taken you off the path here. Here is a newsworthy recent event, right? We talk about the culture of NASA shifting over time, going from sort of the engineering, the research, the science culture to a program or process culture, right? Jared Isaacman, right? Production, thank you. Jared Isaacman's nomination to NASA leadership there. Any thoughts on that? Do you think that could potentially change NASA, or will NASA change Jared?
Yeah. You asked exactly the right question, John. And it's so critical. If Jared surrounds himself, just like Bill Nelson surrounds himself with people that prevent him from talking to people like me, then NASA has no chance of surviving, because Jared is an amazing person. I know very little about him, but I watched the Polaris Dawn mission. I thought that was amazing. And so I have great hope. But in order to understand culture, us that work in the technical sciences, engineering, we're left brain thinkers.
Yeah.
We need the right brain thinkers. We don't think that sociologists, psychologists, we think that's a soft science. And if you read Diane Vaughan's work on Challenger Revisited, her paper on Challenger Revisited, it explains to you how she was trying to help NASA change the culture, and they basically blew her off. And why NASA? I mean, the new shuttle administrator comes in after Columbia. What's the first thing he does? They cancel the behavioral sciences contract that was trying to understand the culture. So they said, we got the CABE report, but you know what? They didn't do a darn thing to change the culture at NASA.
Huh.
Yeah, there he is, coming out of Polaris.
Yeah. Without NASA, by the way, here. NASA wasn't driving this. He was sort of driving this.
Think about this. The one thing that NASA does great right now is train astronauts. This just shows you, when they described the 2 years of training that him and his crew went through, it was very impressive. They trained these astronauts, very rigorous training. They did an excellent job. They're doing it all at SpaceX.
Yep.
Which is why NASA needs to get out of this business and go back to research again.
Okay. That's somewhere we're going to get to. Like, historically, NASA was astronauts. Like, if you were an astronaut, because you went through NASA's big program, you were selected, et cetera, et cetera. There was a transition when it moved more from test pilots into mission specialists, right, where we're talking about scientists and engineers and stuff. But it was NASA. It was training and selecting and putting these astronauts up. And as we get more in space,
think about it.
More companies are going to do this. Go, I'm thinking.
Think about it. NACA. Do we train pilots to fly airplanes? No, the aircraft manufacturers do. This is following in the progression, the analog to the aviation industry. We had barnstorming pilots going around, getting the public interested in flying. We have commercial space flight taking people up suborbital flights. That's the barnstorming for space flight of the future. NASA needs to hand it off to industry.
It's something that I think, like, when we have more companies training astronauts, we won't go into suborbital astronauts versus orbital astronauts right now. That's a whole other show. But like, as more companies are developing these vehicles and flying their own missions, and it's not all flowing directly through NASA, how that works is probably going to be a big sea change for us, right? Charlie, we are 10 minutes over time. Do you have to run right now, or do we have a couple more minutes?
I don't
here?
have to run anywhere. Let's get questions from the audience.
Okay, more questions. This one, I'm going to read this one off my phone because it came to me directly. PAL ramp liberation. Going back to PAL ramp liberation. I don't even know if I can read this one correctly. Was it a repair area? Let me just read it. Did he know that PAL ramp liberation on STS-114 was a repair area it machinered on that external tank and could have been cryo pumping related? Do you know why the PAL ramp liberated?
No. The bipod.
Talk to me about this.
I have a picture. I have a picture on the
Of course you do. I love
on the bipod ramp, but it's in a different. It's in a report. Okay, if you go to the reports, and it's the return to flight report.
Can you grab the one in Discord, Kevin? I don't know if, because there's a couple pictures that have been sent to me here where we're talking about power ramps and it's close-ups of power ramps and stuff.
Yeah. If you go to my von Karman paper, the return to flight. No, go to the return to flight paper in the document section. Kevin, not on the slides, but in the document section.
We are so putting Kevin on the spot.
I know, I'm putting Kevin on the spot. You go to the power ramps, you go to the paper that I sent you, and the real reason for the Columbia. Oh, wait a minute. Was that in this paper? Oh, wait a minute. It's not in this paper.
We can also grab this one offline too. If we don't have it handy, we can grab that.
Okay. Yeah, I'll be looking for the picture, but the shorter answer is, I really believe the bipod ramp came off because of leaking the cryopumped liquid, whether liquid nitrogen or liquid oxygen, found its way into gaps in the bipod ramp.
Right.
Okay. And by doing that, when that happened, I'm trying to look for it, when you have liquid underneath the bipod ramp and you launch, basically no pressure outside, it blows the bipod off. I thought that was the most logical answer. But that was the only location where it had a region where that could happen, where you could have that leakage happening. Yeah. And I have it in one of my reports, but on the spot here.
Let's get some more questions.
I don't think that was the reason for the PAL ramp.
Chris Bergen just joined the Zoom call.
I have it. He has it. Page 17 in the shuttle return to flight following Columbia.
Okay. Kevin, can you grab that? I'm so curious here.
No, this is the most believable. We didn't do enough, but I believe this is the most believable explanation because we lost about 28 to 45 of the bipod ramps, and we did nothing about it.
Over all sorts of flights, number of flights.
Over all sorts of flights.
Okay, like total
so
count.
This was a common problem, but nobody thought it could potentially hit the orbiter. No one did anything about it. Okay.
Right.
See, that's where the difference between a research engineer and an engineer. Okay, so if you could zoom in on that a little bit, Kevin.
Here we go. We have the paper, y'all.
Okay. You zoom in on that. Okay. So what you have is this is a joint in between, and there's an airspace in this region to the left, right? And in that airspace, it's right next to the cryogenic tanks. When you see that orange dome piece over there, in between that's where the hydrogen is. And so what happens is the air in between that space in the intertank region condenses inside that gap, and it leaks into the bipod.
Right.
And it goes and it gets into voids of the bipod foam. And then when you launch, that bipod blows off.
Right.
And now the reason that we believe it only came off the left bipod and not the right is because the right bipod had a porous region that, for whatever reason, the way it was manufactured, allowed that gas to escape. That's why we never saw any bipods coming off the right bipod.
That sounds like the Orion heat shield, gas escaping versus the permeable. Anyways, that's a totally different thing.
That's a totally different thing. But
Similar
anyway,
concept, honestly. Something trapped behind a layer, and the layer popcorning off instead of escaping in a controlled manner. So, anyways,
and you want to know what, John? If you can allow all the folks to have access to my slides and the papers that I gave you,
yeah,
a lot of this is discussed. And if you don't want to buy my book, don't buy my book unless you really want to fix a broken organization. You can read this in the papers that are free.
Yeah, there's
my publisher is going to be really pissed off at me, but I want you could get these papers real quick.
There's no way in 90 plus minutes we could go over everything in the book. It's 300 pages. There's so much discussion of these sorts of stories. We're not like, this is the thing that I could see people having trouble with. Oh, you're armchair quarterbacking after the fact, right?
No.
You just know after the fact. A lot of this, Charlie, is experiences because you were there in the room, you were standing up, you were doing the research, you understood stuff as an engineer, and this isn't just 30 years later armchair quarterback.
So this isn't sour grapes, believe me. When I was reassigned as director of engineering, that was the happiest day of my life because I didn't want to be in that position unless I had the power to really change the culture and do it right. I'd rather not do that. And so the next 15 years of my life is really the second half of the book. I should have wrote 2 books, but I didn't have the time. The second half of the book, these were my thoughts on how do you fix this problem? And we could do another whole series on that. But the second half of the book, before I retired from NASA, when I finally was fed up, I went to headquarters with these experts that I was working with without NASA and gave them a 60-page document and a presentation on how do you change the culture to be a research-based culture, and how do you distribute that throughout the agency and do the training so that you can prevent accidents and prevent tragedies. And when I heard nothing but crickets, that's when I knew it was time to retire. Let's get another question.
I have so many questions
I'm running your show now, John. I'm sorry.
No, it's fine. This is interesting stuff. I think it is resonating with people. Like this is a thing. Bureaucracy slowing things down, engineering information not making it to the places that it needs to be, and we want to go into space, and we want to fly, we want to see rockets go, we want to see people in space, we want to expand.
You're never going to make it happen if you believe what people are telling you at NASA right now.
Yeah,
it's not going to happen because they don't understand how to change the culture.
Okay, I'll toss this out there. We didn't talk about any of this in advance, by the way. Starliner, Butch and Sonny, what's your take on not returning the astronauts that went up on Starliner back on Starliner? Should they never have flown Starliner in the first place? Was that a good call?
No, this is very interesting, right?
Yeah.
Bill Nelson made the right call, right? And I was proud of him for making that call.
Okay.
Right, because it wasn't NASA's vehicle, but it was absolutely the right call, because even though Starliner landed successfully, it had some issues, right? And there were some major reasons why they didn't need to fly back on that. And so he absolutely made the right call. What I believe, I think if Boeing, and I write a little bit about Boeing in my book, but I think if Boeing is really going to be able to change the culture, and I haven't seen too many signs indicating that, if I was the new CEO of Boeing, I wouldn't have let NASA make that decision. I would have said, but it's Boeing's decision that we think that you should fly in another vehicle, and we want to fix our vehicle. And that would have shown everyone in his organization and every one of his stockholders that Boeing was committed to changing the culture. He had the opportunity to do that. He didn't have to have NASA slap him on the wrist. Because if you remember in Thiokol, for the O-ring decision, the Thiokol engineer said we shouldn't fly. Then they were strong-armed by NASA. NASA program managers saying, well, when are we going to fly? When are we going to wait till it's April?
Right.
And they came back with a new decision, right?
What's the pressure?
Their decision.
what's the pressure on NASA people there? Like you talked about them coming up with a flight rationale, which is like a story as to why it's okay to fly.
Want to know? Yeah.
Not driven. What's the pressure to fly so much? It seems
Think
like they
about
barely
it.
fly.
Think about it. Right. And so their decision to not use the Apollo heat shield is
Right.
because it takes too long. It takes too long to manufacture, and it costs too much, right?
It doesn't
Well,
feel like they're very
yeah,
quick with the manufacturing right now.
Right. They fly maybe once a year if they're lucky, and it costs $4 billion. So how much does it cost for an engineer to put Avcoat in those honeycomb panels?
Right.
Right. And so why? No, it's a good question. Why fly now? Why make the decision now before the new administrator comes in? Because they want to lock in. This is just my opinion. It's just my opinion. They want to lock in that decision to keep the money going to the same industry base that's building SLS, because there's a lot of people questioning whether or not they should cancel the program. The decision is made to keep the program going, is my opinion.
Right. And it feels like I am a space consumer, right? I'm not making these decisions.
Well, let's ask someone. Is there a program manager? Is there the administrator? Is there the deputy administrator in the chat that they can come online and?
I don't know their YouTube usernames if they are, but I would certainly.
I can tell you, Bill Nelson.
Yeah.
Let me see, Pam Melroy, Jim Free, Howard Yu. If you're there, sign in, man.
I would be happy to set that conversation up, but
don't eviscerate me in the press. You have your chance to question me now.
I can see how it needs to be a balance. Like, you need to be able to take some risks so that we push things forward, and it feels like SpaceX does a good job of taking those risks when it is constrained and the risk is low. We're not risking lives and that sort of stuff. We can't just shut down all human spaceflight forever, right?
No.
Versus don't fly until everything's 1,000 billion% safe.
Exactly. And that's not what I'm saying.
By that, right?
Exactly. And that's not what I'm saying.
Yeah.
But when you know there are risks that you could easily fix.
Yeah.
Fix them the right way. The reason why they're not fixing them is they don't know how to, and they don't know how to create the high-performing teams to solve these problems.
Right. Gotcha. And that's
the problem.
To circle it all back around, full circle, that's what you talk about in your book, Mission Out of Control. We can't cover every single thing in the book. The link is in chat if y'all want to hear more of Charlie's thoughts and stories and engineering analysis. There's graphics in there, there's diagrams, there's flowcharts, there's engineering related stuff, and there's cultural related stuff, right? So is it a silver bullet? Always take things with a grain of salt, make up your own decisions and stuff like that. But if you're interested in hearing more about Charlie's thoughts here, the book is out there. The papers are out there too, right, Charlie?
And let me say this about the book. I decided to write this book before the Artemis heat shield problem, right? Okay. I'm not doing this for myself. I wrote the book, and I understand if NASA doesn't want to talk to me, that's okay. But for people that want to solve this problem, and it is a complex problem, to change it, to transform an organization and to transform a culture, I would love to do research on this. We're working with people at the London Business School. Amy Edmondson, I'd love to work with her students in the Harvard Business School to do research to help solve this problem. I wanted this to be the second half of the book. Is my thoughts and my team's thoughts on how do you solve this problem. I want to open it up for a discussion. I'm thinking of starting a podcast where really good people that have been trying to solve this problem for a long time could weigh in.
Oh, Charlie, I like this. By the way, the QR code is if you want a signed copy. You can just use the Amazon link to grab a copy, but that's for a signed copy, right?
No. There's a link in there for the unsigned copy also.
It's both of them. Okay,
the
cool,
Amazon.
Gotcha.
Yeah.
If you want a signed copy, you can get a signed copy. There are two things here, two possibilities, right?
I'm not doing this to make money on the book. Believe me, you don't make money on books.
It doesn't sound like it. There's two different things here, right? There's changing the culture of ingrained, entrenched, existing organizations, your NASAs, your Boeings, this sort of stuff. There's a lot of stuff being done in space these days by new companies. And so
Yes.
maybe it's not changing the culture of an existing organization. Maybe it's a new organization that wants to get stuff done. And that's another application for these things that you're talking about.
You're hitting the nail on the head. And so I'm going to give another plug to another great behavior person.
I love how you're plugging everybody except yourself.
Organizational behavior. Gary Hamel wrote a couple of books, Leading the Revolution, and his new book is Humanocracy.
Right.
And he wrote a free paper that everyone could get called Why, in Harvard Business Review, Why Bureaucracies Must Die.
Right.
And you're absolutely right. If you think about it, when we developed Space Shuttle, we had dozens of space companies that were doing innovative things.
Yep.
Then all of a sudden they got eaten up and we had maybe 2 or 3 companies, Boeing, Lockheed, and that was it. ULA, that was it, which was a combination of Boeing and Lockheed. Now what you're seeing happen is these bureaucracies, these entrenched bureaucracies are being outdone by these younger, smaller, newer companies, more competitive, more innovation, and that's one way of killing these dying bureaucracies. So my answer for these bureaucracies, if you want to be solvent, if you want to have a company, if you don't want to go away, is you need to transform your organization.
Right. I think we've heard a lot. We've heard a lot of that. And upcoming changes in NASA, will it transform? Will the culture change? Somewhere in the middle, we'll see what happens. We can't answer it right now. We don't have a crystal ball.
Gotta cross your fingers. Yeah.
But we'll see. Did we get Chris on the call here? We're at the end of the show. I don't know if we actually got Chris on the call.
Voice check.
Charlie, can you hear Chris?
Who is Chris? Chris who?
So Chris is the founder of our organization here. So reporting on Shuttle for 20 years now. Chris is like frantically texting me in the back channel. How you doing, Chris?
I'm doing well. I want to ask Charlie a question. It's been a fascinating chat, and just so many things have brought back memories. So many memories, because I was reporting from Return to Flight onwards. So I covered your mission. And when I saw the PAL ramp come off live, I was the same as you. I was like, we literally watched it live on NASA TV. We're like, oh no, not another phone liberation. And we're all playing back the video, trying to see if it hit anything, because we were just so glad it avoided. But I want to ask you a question, Charlie, that I'm desperately wanting to ask. Right? So, RATIF, you've got all these safety improvements where you've got inspections on flight day 2 with the OBSS. You've got the RPM under the ISS. You've got all the data, the data team, the damage analysis team, everyone checking everything on the TPS. So you've got the safe haven if they find something wrong, where you've got 6 months before the next mission, the CSCS and launch on need. Go back to 2008 and 2009. I'm going to make you the NASA administrator for 2008 and 2009, knowing what you know, and knowing there was no safe haven, and you had to have Endeavour on the other pad, ready to rescue Atlantis' crew, would you have flown the Hubble rescue mission? Would you have flown the Hubble servicing mission on STS-125?
That's a very good question, Chris. And you want to know something? The high performing team that I described in my book and how it transitioned from Don Pettit's laboratory garage to Steve Scotty at NASA Langley Research Center, they did the impossible. And so they had a large area repair. And I could show you that slide if you have time.
I love the slides, Charlie.
I will show you this slide. If you go to slide 71, Kevin.
We'll get slide 71 in just a second, folks.
And so, Chris, Chris, on the Hubble mission, because my good friend Mike Massimino, I believe, was on that mission, you definitely wanted this repair technique, right?
Yeah.
And remember, the program office said this was not a requirement to fly. This wasn't a necessary condition to fly, but I believed otherwise. Steve Scotty, if you look at the lower right-hand corner, worked with a team of people, and we describe how we did this in the book, and came up with a large flexible patch over a wing leading edge. And look at what it's held down with. It's held down with those small plugs that we designed to drill and tap holes in the wing leading edge to secure that. And this was a no kidding. We didn't have time to test this to see if it would work. But if you're desperate and that's your last attempt, like the crew on STS-107 didn't have an attempt, in your toolkit was a capability to do that kind of repair.
To do something.
To do something.
Do
Yeah.
something, right?
Yeah.
It's crazy because this was the mission, because of the orbit, that had the biggest risks of MMOD damage.
Yeah.
You know, if you're going to get damage on an orbiter's TPS, never mind ascent, you might have got it in the orbit when you're rescuing, capturing Hubble, because the MOD in that orbit is higher than a mission to the ISS.
Hey, you want to know how else you can get damage? Kevin, show the bird strike video.
The bird strike video.
This was the other near miss that we didn't talk about, right?
Yeah.
This is the other near miss. Look at that. We almost skewered a vulture right off the pad. If that vulture, you can even see him like smoking as it's going through the plume. If that vulture would have went over the other side of that and went through the windscreen, we would have been the first return to launch site abort in the history of the shuttle program. And Chris, you probably know what the odds of that being successful is.
Not very highly likely. I think the best chance of RTLS working is trying to bail out over the SRB. You know, not going to actually get back to the landing site now.
Good.
Oh, wow. Charlie, in chat, I know y'all have probably seen me on camera and I'm looking down at my phone. And on occasion, this was Chris frantically telling me things that he wanted to pass on. And I was like, hey, just join the call yourself.
Hey,
I figured
Chris,
you'd be cool with that, Charlie.
Chris, you could call me anytime. I'll be happy to answer your questions.
Thank you, Charlie. It's awesome. What a brilliant interview.
Yeah, gosh. We're now 30 minutes over. Like I said, we put the link to the book in there in the chat. We're going to go, it's also in the description of the vehicle, description, talking about vehicles too much, description of the video. If you want to get caught up and you want to read more about Charlie's books and findings and research and all the different things that you've gone through, Charlie, it's in the book there, Mission Out of Control.
Hey, could I say one more thing, John?
Of course
if they go on the site, they'll be able to access this interview. And will they be able to leave comments? Is there some way that we can create a thread to have this discussion, going? Okay.
Yeah. So it's going to be archived here on our NSF YouTube channel, and after the fact, people can watch it and they can leave comments or feedback, and I can send you a link to that. If you want to answer people's questions in the comments afterwards, I will happily send you that link.
Definitely.
Not a lot of guests do that, and it would be amazing if you popped in and did a little bit of follow-up question answering.
No, I'm very interested because I was opening up these discussions and raising these discussions on LinkedIn, and I have people that are chatting back and forth. No one from NASA. I would love to have people from NASA
I get it.
actually sign in.
Waggling eyebrows.
But yes, I would be happy to do that.
Yeah. In any event, I think that is good at 30 minutes over schedule here. Charlie, I'm going to work very hard to have you back on the show with us in the future. I would love to show you some of the things that we see out at SpaceX with the Starship things that are going on, the TPS changes and stuff, and just get your feedback on how that's going to work for SpaceX. You want to talk about it live? While a Starship is re-entering and tell us what you're seeing live, we could set that up too.
I would love to do that. I would love to get a tour of the facility. I would love to meet with the engineers working on Starship. And
a little outside of my purview on that, but yeah.
But yeah. No, anything you can get me, I'll read it and come up to speed.
All right. Chris, you good?
Yeah, very good. Thank you.
All right. Folks, we talked about the book. We talked about Charlie. This was a spicy and emotional. It was a very interesting show. I know there's a lot of different feelings and things you want to, like Charlie said, think that NASA is the shining castle on the hill that can do no wrong. And then the curtain gets peeled back and you see these processes and you question, why haven't they shared that information with us? At the end of the day, we want to be in space. We want people to fly in space, not just NASA, private companies. We want it to happen safely, but we want it to happen, right? And so the things that Charlie is talking about are things that should be taken into account and things that you should think through. And maybe they're not all perfect answers, but thinking through it. And I especially love the concept of getting engineers and scientists that direct line into making decisions and being right there. Don't layer in 80 layers of bureaucracy that loses the important signal in the noise or communication of bureaucracy or program management or whatever. This is my opinion that I'm talking now, but at the end of the day, I want to see things fly. I don't want us to be paralyzed by safety and aversion to risk, but I also want to do it as safely as we can with the tools and technology and stuff that we have. What is our next show next month? We've got another one. Oh, we don't have one next month. It's January. The next time we do an Astro Live, I will be on site at the Intrepid Museum in February, and that is going to be Kids Week. Y'all know we're out there. We're trying to get new engineers involved. And so Intrepid does Kids Week every single year, and I love to go out there and see all the booths and stuff like that. But that is coming up in February for Kids Week. This one, of course, was the name of the show for Astro Live, From Tragedy to Transformation, Lessons for a Future Safer in Space. Charlie, I really do appreciate you spending time with us here this weekend.
Thanks for the opportunity. And one thing I wanted to say,
of course,
John, I'm going to be in New York in a couple of days.
Okay.
At an event, and hopefully you could add that to the link. I'll be near Hudson Yards. It's the Terraverse Salon event. It's going to be near the Navy Yards. And I'm going to be speaking to an audience of about 200 people live. Yep. And so I know it's sold out already, but if people can get there or want to meet with me, I'll be in my favorite city, one of my favorite cities, New York City.
All right, that's coming up next week or something, right?
It's going to be on December 17th or 18th.
Okay,
December 18th.
All right, gotcha. We'll get a link. We'll see if we can get a link for that as well. If there's anybody in New York who can come by and see in person, but that is going to bring us to the end of our show today. Clearly, not the end of the conversation. Charlie, I hope we have some opportunities in the future to talk with you again, but thank you so much for taking time out of your Sunday to sit here and tell us some things that I think maybe a lot of people might not want to hear.
Thanks for having me on, John. I appreciate it.
All right, good deal. Folks, that's the end of the show. You know what to do. If you'd like to get back to the channel here, like and subscribe or something. Some of these shows that we do are sort of hidden gems. It's not the Starship launch or the big exciting crew mission or anything like that. But stories from people who know, from people that are there, engineers that worked on stuff. That's what we do in these sorts of shows. So if you liked it, share it with a friend, send it around. Maybe look through the back catalog. We've got a lot of interesting conversations on there, too. But for now, that's the end of our Astro Live event. Dr. Charlie Camarda, thank you so much again, and we will see you nerds later.
And here we go.
Propulsion continues to be nominal.
RS-68 chamber pressure looks good.
Rolling up. Roger, roll, Atlantic.
Water towers, fly! Yes! Tango down to nominal.
Fighting down to SPD off. Bring in SPD off. Off. It's orange! Orange 45! Oh my god! Oh my god! Decollage! Look at this! Put that in the big bag, Jingle.
343 unfolds to go.
Indeed.
We rise together back to the moon and beyond.
This is methane to be igniting with the flare, correct?
Yikes. You bet. Sure. We don't need any more of these.